Okay, so what we had found that in this system, this height was equal to some constant times the T. Now, from now on, I will always use the Kelvin units. I will never use the Celsius, never use the Fahrenheit, just the Kelvin units. So when I write the H is equal to some constant times T, this T is always in Kelvin units. But we also know that this height is nothing but a measure of the pressure of the system. So in a sense, the pressure, or let's say since we assume that the volume is constant, the number of particles is constant, this ratio is some constant times the temperature, or PV over NT is equal to some constant which we will denote by R. So this is the ideal gas law we have. The pressure of an ideal gas times the volume of an ideal gas is always equal to the number of gas, amount of gas you have in moles times R times T. Well, this N we have in the ideal gas law. N is defined as the number of gas molecules. N is the number of gas molecules we have divided by the so-called Avogadro's number. And this Avogadro's number is a huge number. Well, as I said in the previous lecture, at the end of the previous lectures, in physics we don't like these arbitrary numbers. So rather than using this mole number is defined in terms of the Avogadro's number. It's an arbitrary number, in fact. So instead of using the mole number, what we work with is the number of molecules we have. So we have PV is equal to N times this R over NA times T, which we define as the total of the number of molecules times this constant, which we call the Boltzmann's constant, N times Kb times T. Well, we still have some arbitrary number here. This Boltzmann number will also be an arbitrary number. We will see how if we want, we can also get rid of that one, the Boltzmann number, but we will see in a moment. So this is the ideal gas law we have. So if you have a gas, experimentally, we know that under certain conditions, that is, they should be hot enough, they should be diluted enough, the pressure, volume, and the temperature of the gas and the amount of gas we have are related through this relation. All the gases are related in this form. Satisfy this equation, all of them. Now, then the question is why? Okay, we have made this observation, but do we have an explanation for this? Now, if I would ask you the temperature, your friend has already said that, it is the energy. And I'm sure that if I had asked you, more of you, you would have told me that, okay, temperature is the measure of the kinetic energy of the molecules. Why? So that is the question that we would like to address now. How do we know that temperature is related to the average kinetic energy of the molecules? We do know. In a sense, we also define it. But on one hand, we have the ideal gas. Remember, the ideal gas law was before we discovered the atoms. So we define some temperature over there. Now, then we have once we have the molecular picture of matter, now we know that the gas is made up of small molecules which just move around. So if you have a container filled with gas, well, it is just a collection of molecules which just move in random directions. Each move randomly around. They all move randomly. So this is what we have for the gas now. And after we had a concept of the temperature, now we can talk about the kinetic energy of these molecules, and it turns out that the kinetic energy of these molecules is proportional to the temperature. So let's study this system from this point of view. So we have a bunch of molecules or atoms, almost point-like. They just move randomly around. So as a first approximation, we will just ignore the fact that these atoms will collide with each other. So we just ignore their collisions. So they just move randomly. If you just take one of them, you take this one, it will just hit here, bounce back, hit here. So this is the kind of motion it will make. And so on. Now, when it hits this wall, let's say, we have our molecule. It has some speed v. It hits the wall. We will assume that it bounces elastically. After it hits, it will have this velocity. So what happens is initially it had the x component of the velocity. Let's call it vx. So this is the x direction. So what happens, it just hits the ball and bounces back. The only thing that changes is the x component of the velocity. So vx just becomes minus vx. So the change in the momentum of this object, let's just write the magnitudes. Well, its speed changed by 2vx. So the change in the momentum of my molecule is m times 2vx. This is the change in the momentum of a single molecule. So if we have this container, and inside this container we had a single molecule, and the pressure, remember, the pressure is the force per area. Essentially, it's a force. So you have, let's just imagine, we have this container. There's a single gas atom molecule. It just moves around. And this is one of the walls. So if you measure the force acting on this container, what you will see is, okay, so it comes here, it hits it, it exerts a force. Well, its momentum is changing. It means that the wall is exerting a force on my atom. But that also means that my atom is exerting a force on the wall. So it exerts a force. So if you measure the force here, the force as a function of time, you measure some force, and then it bounces around, comes here, hits it again. You measure another force, moves around, comes again. You measure another force. So this is what you, in an ideal situation at least, this is what you would have measured if you would measure the force acting on this wall. It will not be a constant force. It will just tick, tick, tick. Now, of course, never we have a single atom in a container. We have like on the order of 10 to the power 23 atoms. And each one of them will hit this wall at different times. So you will have one hit due to one ball. Then you will have another hit over here, another molecule, another hit, another hit, another hit. So on the average, what you will see is you will just measure a constant force acting on the wall. Now the average force, let's denote it by this symbol. This brackets will just mean it's an average. Now the average force total force will be nothing but n times the average force of a single atom throughout this process. Well, what is the average force of a single atom? Well, it is remember the definition of the force exerted by an object as its momentum is changing. So that if average force is the change in the momentum divided by the time it takes for this change to happen. Well, the change in the momentum, we had already seen that it is m times 2vx. Now, the amount of time it takes, well, when we are making this average, we are not making an average over a very short time. So for a single atom, the collision time will be very small. But what is the time it takes for one atom to hit and hit it again? So this will be the critical thing, the important property. So we have, remember, we have this cube. This has side A, this has side, let's say, L. So if this is the case, then delta T, so we have this single molecule, it hits here once, bounces around, comes back and hits it again. The time difference between these two hits, well, the total distance it covered in the horizontal direction is nothing but 2L divided by its horizontal speed, the horizontal component, its velocity is Vx. So this is the average time, the time between two hits. So the force, the average force throughout the motion of this single molecule is m times 2Vx divided by 2L divided by Vx. Or the force is mVx squared divided by L. This is the average force exerted on the wall by a single atom. Well, we have n of them, so the average total force acting on it. Average, because this, we know, we had just discussed that at least for a single atom, the force will be fluctuating. Well, it will have peaks, separate peaks. If you have many atoms, the force will be rapidly fluctuation around some value. If you just average them, you just get that value. And that is in fact what we are measuring. We are not able to measure so fast variations. And this is equal to mVx squared over L times n. So this is the total force acting on this wall. Well, we know the definition of pressure. Pressure was equal to the force divided by the area. Well, force we had just calculated, so this is equal to n mVx squared divided by A times L. But remember, now we are, for simplicity, we have just assumed the cube. This length was L. This has area A. So A times L is nothing but the volume of this system. So P times, this is nothing but the volume. So P times V is equal to N M Vx squared. Almost. Compare it with PV is equal to N KB times T. So this M times Vx squared is nothing but N times KB times T. Well, there's one catch over here. We took one single typical atom, and this was its velocity. So if you have many atoms, since each one is moving randomly, the x component of their velocity will also be completely random. So the Vx squared over here should be kind of an average over all of them. This is the average of the x component of their speed squared of all the atoms. Well, what is so special about the x direction? Well, you see the pressure depends on the x component. So what is special about the x direction? Trust the force inside you. You know the answer. Hmm? It doesn't matter. X direction is completely arbitrary. So what if x direction is completely arbitrary, the average speed squared of the components along the x direction is nothing but, it should be equal to the average of the y components squared, which should be equal to the average of the z components squared. They should all be equal. There's nothing special about the x, y, or z direction. But there's sum. If I take the vx squared plus vy squared plus vz squared, then that is nothing but v squared. So each one of these is nothing but the average of v squared over 3. Because each one is equal, their sum gives me the v squared. So this tells me that PV is equal to n times mv squared average. Well, let me put a 1 over 2 over here, times 2 over 3. Well, you should have recognized this ratio, this quantity over there. 1 over 2 mv squared is nothing but the kinetic energy of my gas molecules. So on one hand, we know that we have seen that PV is n times 1 over 2 mv squared times 2 over 3. We had this picture of the gas as a collection of molecules. On the other hand, we know that this thing should be also equal to n times the Boltzmann constant times the temperature. Well, this is what we had derived from this microscopic picture of the gas, and this is what we had measured in experiments. So, and they are both should be equal to the same quantity. So they should both be equal. But that also tells me that the average kinetic energy of the molecules inside my gas should be equal to 3 over 2 kb times T. Now we know that the temperature of an object is actually the measure of the average kinetic energy of the gas molecules, of the molecules making the object. Now we have the proof. So any questions up to this point? Yes? So let's go back to one page. A few pages. So let's go over what we had done. Still, let's go over what we have done. We had this wall. We had this container filled with gas. So what we wanted to do was to calculate the pressure. Well, to obtain the pressure, we need to measure the force acting on the wall. So we want to find the force acting on this wall. Well, the force, if I take a ball, hit the wall, it bounces back. So I can calculate the force exerted by the ball on the wall by just calculating the change in the momentum of my ball and the time it takes for that change to be realized. So this is how we define the force. The force is the change in the momentum of an object. This is the average force. Well, the momentum change of the single atom, it hits with an x component equal to m times vx. This is the x component of the momentum. And when it bounces back, it has minus mvx. The y and the z components, they do not change. So the change in the momentum of my ball is in this direction, minus x direction, and it is m times, well, twice mvx. So that is the change in the momentum of my gas molecule. Agreed? Now, this delta T, When we are talking about the average, okay, this is the delta T. You should have objected, saying that, okay, the ball collides with the wall, the molecule collides with the wall in a very small amount of time, delta T. Why did we take such a huge amount of time? Now let's go back here. We said that, okay, if we have a single molecule, we will have all these black lines. So we have a peak, another peak, another peak. If we have many of them, they will just average to a constant value. So the force acting on the wall, we can just say that, okay, it is the average force acting on the wall, the average over a very long amount of time. Yeah, it is constant. So you can say that it's an average over a very long amount of time. So that is how we can define this force, this average force acting on the wall. The force acting on the wall is equal to the average force acting on the wall on a very small amount of time, very large amount of time. Now, if I make that definition, within that definition, I'm defining the force exerted on the wall as the average of the force over a very long amount of time. Then I can make this definition. I can write it as the sum of the n times the average of a single molecule. Otherwise, these two has nothing to do with each other. If I would define this as an average over a very small amount of time, well, this F is just flat, constant, whereas the force exerted by a single molecule is just some number here, 0, some number here, 0. So these two things can never be related with each other. Only if I define these averages over a sufficiently long amount of time, I can write this equality. So what is that amount of time? Well, as long as you want. But in this case, within each 2L over Vx time, the momentum change is delta P. If I wait, I don't know, 10 times this much, the total momentum transfer to the wall will be 10 times this much. So I don't need to wait that long for a single molecule. But it's enough for me to wait until it starts repeating the motion. So that is why we take this delta T is equal to the time it takes for a single molecule to hit the wall twice between two collisions with the wall. Well, how much it takes? Well, it starts here, moves here, then comes back. The total distance it covers is L. And the total distance it covers is 2L, and delta T is 2L over Vx. So you just put it there. So the average force exerted by a single molecule on the wall is m times Vx squared over L. Then I can use this one. The total force exerted on the wall is just n times this quantity. Now you can ask, okay, so we derive this result for a cube. What about some arbitrary shape? It is a nice exercise. I do advise you to do it. It will not be a homework. But for a sphere also, you get the same result. The result doesn't change for a sphere. So we know the force. We obtain the force, the average force acting on the wall, divided by the area. Then you get this L just becomes the volume. So we obtain this relation from this microscopic picture of the molecule, of the gas. On one hand, this is for Vx squared, but Vx squared is equal to Vy squared is equal to Vz squared. And PV, so you can just replace Vx squared by the average the average of the square of the speed of my object divided by 3. And so the pressure of the gas times the volume of the gas just turns out to be equal to the number of molecules I have times the average kinetic energy of the molecules inside the gas, times 2 over 3. So this is what we had derived using kinetic theory, using this microscopic picture. And this is what we have from observation. From our definition of the temperature. Remember, we define the temperature using the ideal gas. So this is the definition of the temperature in a sense, or you can say observation. So this quantity and this quantity, they have to be equal to each other if our description is correct. And that tells us that the average kinetic energy of a molecules inside a gas is in fact directly proportional to the temperature of my gas. So from this relation tells us a few things also. The minimum possible value of the kinetic energy of a molecule is 0, classically speaking. So this T can never be less than 0. This is why we call this the absolute 0. You cannot go below that absolute 0. Question? Now, the speed of the objects. Now, if you look at the gas molecules, they will all be moving randomly. And even their speeds, okay, this is the average speed. Each one will have a different speed. And you can talk about the speed distribution of the molecules. And the speed distribution is mainly has such a shape, more or less. So what this tells me is that, well, this is more or less the average speed, VRMS, let's say it. Now VRMS, we define it as the square root of V squared, average. This is the definition. It's kind of the most probable speed. Although most of the atoms will have speeds close to this RMS speed, some of them will be very small, some of them will be quite fast. Now, if you calculate the speed of, I don't know, typical things, they are slow. The RMS speed is not that fast. Well, faster than the speed of sound, I think, but it's slow. For larger molecules, it's even smaller, the velocity. But I'm sure it's your experience that if somebody would be eating some onion on that end of the room, you would smell it from here almost immediately, right? You never experienced that? Didn't you ever take a bus to go to cities? Somebody would be eating onions. Well, that is because we have this tail. Some of these smell molecules that cause the sensation of smell, are traveling really fast. So it's almost instantaneously we get the smell. It doesn't get intense because most of them are much slower. But with time, I mean, it will get intense. Okay, any questions on this one? So now, we first define the temperature. Now we know that the temperature is the average kinetic energy. Before the break, I just would like to discuss one more topic. Can you bear it? Just some stretch a bit. Okay, let's discuss another force. Okay, the pressure was one kind of a force that we discussed. But before, we had also discussed another force. We said that the drag force was inversely proportional. Well, okay, it was proportional to the speed of the object. Now we can derive this with this microscopic picture of gas, at least for the gases we can do it. First we should identify the source of this drag force. Now let's just imagine we have some object in some gas. So this is all the gas molecules around. They're all moving in random directions, etc. And on the average, we know that the pressure on the left-hand side acting on this wall, on this object, should be equal to the pressure on the right-hand side. So the net force acting on this object will be 0, right? If it is at rest with respect to the gas. In this microscopic picture, what will happen our description now is the amount of molecule, the amount of momentum transferred to my object due to the collisions with the molecules from the left should be equal to the amount of momentum transferred to my object due to the molecules that move, that are on the right. So they will all collide with the surface. They will all transfer some momentum. And on the average, the momentum transferred from the left should be equal to the momentum transferred from the right. So the average force is 0. The net momentum transferred to my object is 0. Now let's do something else. Let's suppose that my object is moving. Now it has a speed. Well, it will collide with objects on the left and also on the right. Now let's see, in a simpler case, let's just remember we studied the collisions. Now this is an object which is much, much more massive than an individual gas molecule. So it is as if an infinitely heavy object collides with an object that is very light. So let's say this moves with some speed v. Suppose that there is an air molecule that moves with speed v1. They collide head-on. And when it bounces back, do you remember its speed? It will be 2v minus v1. Remember, if my object is not moving, if this was at rest, v1 hits this one, then bounce back with the same speed, just the direction changes. So that is why we have this minus over there. So the momentum change of this v1 is nothing but twice m times v minus v1. Right, this minus this one, yeah, the sign, okay. So that is how much the momentum, this is the momentum change of my gas molecule. This is also the momentum transferred to my object as it collides. Now let's look at the other case. Other case meaning that there is a molecule on the left-hand side. This one. Yes. You can look at it like this. Suppose that you start moving with the velocity v with this block. Okay, so you change your reference frame. In that new reference frame, this block is at rest, and this moves with a speed v1 plus v, or v1 minus v with the vector signs. Okay, so it hits this object with speed v1 minus v1, no, v1 minus v, and when it bounces back, it just reverses the direction. But then so its speed after the collision is now v minus v1. But now we need to go to our original reference frame. If we go back to the original reference frame, we have to add another v, that is 2v minus v1. I mean, you can just use momentum conservation, energy conservation, blah, blah, and you can just review this. It is 2v minus v1. Okay. Now let's look at the other one. We have this other one, v2. It will hit this one. Well, we will assume that it moves slowly. It moves much slower than the average speed of the molecules. So it hits this one. It will bounce back. And when it bounces back, its speed will be it will be 2v minus v2. Well, now you should complain. How come? Okay, let's write the in terms of components. So this is my x direction. So V1 is equal to minus the magnitude times in the x direction. Okay, so delta P1 and V is equal to V in the x direction. So V minus V1, the magnitude is 2m V plus V1. So this is the change in the momentum due to the change in the momentum of this molecule. Now V2, on the other hand, is V2 in the x direction. So the change in the momentum of the second molecule will be equal to twice m V2 minus V. Yes. I'm in this reference frame. Yes, so there is this, we are filled with this gas, all the gases around us. So I take this object, I just move this object with some speed v. As this is moving, I have this, there's a molecule over here, they collide and it bounces back. There's also this molecule over here, it collides and bounces back. No, this is my reference frame. And this one is, you are the reference frame. And this one is moving, yes. 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 Two V minus V1. Why? No, both of them are correct. But you see this. Now you see this 2V minus V1 is 2V plus V1 in the x-hat direction. And here this one is 2V minus V1, V2 in the x-hat direction. Now this sign difference over here is due to the vector nature of the velocities. So this velocity vector is in this direction, and this velocity vector is in this direction. The relative velocity of this molecule, the relative speed of this molecule and this object is larger than the relative speed of this molecule and this object. So in fact, that is why when they collide, remember in elastic collisions, the only thing that changes is the sign of the relative speed. So the relative speed here is larger, and it changes, transferring momentum to my object. So the momentum transfer due to this molecule on my object is larger than the momentum transferred by this molecule hitting my object, because the relative speed between these two objects are smaller. And these are the momentum transfers. And just remember, on the average, V1 and V2, they are equal. They are the same quantity. So they are the average speed of the molecules, the typical speed of the molecules. So we have this object. We have a collision here. And this is our x direction. So the change in transferred momentum due to this collision is twice m v plus v1 in the x-hat direction or the minus x-hat direction. Now let's put back the vectors. Minus x-hat direction. The momentum transferred to my object. That's in the minus x hat. This is due to this collision. Then there's another collision over here. And the momentum transferred in that collision, well, there's a minus sign over here, is plus 2m v2 minus v. In the x-hat direction. So the net momentum transfer well, just sum the two. You will get twice m v2 minus v in the x-hat direction minus 2m v1 plus v in the x-hat direction. And remember, v1 is equal to v2 on the average speed of the molecules on the left and on the right, they are equal. So these, what we will obtain, v1 and v2, they will just cancel each other. You get minus 4mv in the x-hat direction. So the momentum transferred to my object is proportional to the velocity of my object. This is due to collisions of one atom on the left, one atom on the right. On the average, it will make equal amounts of collisions on the left and on the right. So you just need to sum the average over the contributions of all of these ones. But at the end, also divide by the average time. The force is delta P over delta T. But whatever you do, delta P, which is also proportional to the force, will be proportional to the V. The force the drag force is proportional to minus V, with some constant that depends on the mass, and it will depend on other properties of also. Now, to find the proportionality constant, well, I will not go over the details, but to find the proportionality constant, you can just say that, okay, let's just imagine some time dt. Within this time dt, it will collide with molecules in these volumes. And then you can calculate how many collisions are there, how much momentum is transferred in this amount of time dt, the total momentum transferred on my object in this time dt. And once you have that, divide by the momentum transfer divided by dt, you will get the net force acting on my mass. So it will still be in the direction of the minus p. For small velocities, remember we use the fact that it is moving slower than the average molecule. So if it starts moving faster than the molecules, then of course it will not be able to collide. The number of molecules that it will collide on the left-hand side will be almost zero, because it is moving faster than any molecule, so molecules cannot catch it from the left. So this will be significantly modified if it starts moving fast, but for small velocities, small speeds, this will hold. Any questions? Yes. Well, it hits and bounces back. So it had an mvx in this direction, and then when it bounces back, it has minus mv in the other direction. The difference is 2mv. Here there is no friction. Yes. So because this tells us that there is a force acting on an object moving in a gas, which is in the opposite direction to its velocity, and it is the magnitude is proportional to its speed. No. Well, depends on how general you define the friction. You can say that the drag force is a kind of friction force. Because you see, what happens here is that you will be losing your energy. The kinetic energy of your object will be lost. So what happens to it? Well, there are all these molecules on the right-hand side which are, their kinetic energy is increasing. Well, there's also the decrease on the left-hand side, but the increase is much larger than the decrease. So the average kinetic energy of the gas is increasing as you move your object in your gas. But we just said that the average kinetic energy of a gas molecule is nothing but it's a measure of its temperature. So as you move this object, you are increasing the temperature of the gas. And that we call heat, by the way. Heat is not temperature, but the amount of energy you transfer to an object. That is not the kinetic energy, is what we call the heat. No, I don't see that move. Can you speak a bit louder? Yes. The temperature increases a lot. Well, let's see here, the speed of the object doesn't play any role. Well, the speed of the gases, they just seem to cancel. Now, I'm sure the temperature does have any effect, but this is just a simple model of what's going on. And in this model, at least, we cannot catch the effect of the temperature, if there is any. Well, I'm talking about the magnitude of the momentum transferred. It should be a positive number. And we said that the object is moving slowly, so V2 is larger than V. Well, because this is a vector. This just tells me that V2 is larger than 2V, so this is a vector that points in that direction. That is what should happen, no? You have an object moving in this direction, then it moves in the opposite direction, so the momentum transferred is in that direction. Well, this is something nice about the vectors. In vectors, you don't need to worry about the direction of the things. This thing can be positive, negative, I don't really care. This will be true whether these are positive or negative. But here I should pay attention to which one is positive, which one is negative. So let's give a break then.